I'm sure that everybody's looked at enough IR spectra by now to know that the carbonyl stretch for an aldehyde or ketone usually comes out between 1715 and 1720 reciprocal centimeters. And you can see here in cyclohexanone, the carbonyl stretch is at 1715. However, if you have a double bond here, what that does is it weakens the carbonyl bond, right, because of resonance. Right, that means this bond is going to have some single bond character. And you probably remember that wave number is proportional to bond strength. And so since the bond is weakened, it's going to have a stretch at a lower wave number, and we see that here. So conjugation means you're going to have a stretch at a lower wave number. If you have a strained ring, so as you start to go from big rings to small rings with a ketone, for example, you can see here that ring strain increases the wave number. So we go from 1715 to 1745 to this cyclobutanone, which is all the way up at 1780. And also, when I was a student, the way I remembered the aldehydic stretching was that it occurred at 2750 and 2850. So we have our aldehydic CH stretching, meaning this stretch comes out at 2750 and 2850. In your textbook, though, he's saying that there's just two signals between 2700, and he actually changed it to 28. Oops, where's my pen? From 2700 to 2850. Okay, and I guess that's probably more accurate. But again, I always remembered 2750 and 2850, and you can see those here. They're not super pronounced, but you can see them here in the green boxes. So aldehydic carbon-hydrogen stretching, that's something we can always look for. Now, a carbonyl doesn't have any protons on it directly. However, a carbonyl will have a de-shielding effect because of the dipole going this way on your carbonyl. And so what happens is that if you take these methylene protons, we learned in the NMR chapter that the baseline for methylene protons would be around 1.2 parts per million. But the de-shielding effect of the carbonyl is going to increase their chemical shift by 1 part per million. And so you can see that these protons, if we take our baseline, which is 1.2, and then we add 1, we get 2.2 parts per million, which is shown right here. And of course, that's just an approximation. Next, if you have a singlet in your NMR around 10 parts per million, that's usually a dead giveaway that you have an aldehyde. So it's usually a singlet around 10 parts per million. So you can see that this compound is an aldehyde. Here it says around 9 or 10. I usually think it's closer to 10. And then finally, if you're looking at a carbon-13 NMR spectrum, carbonyls are usually easy to spot because they produce a weak signal around 200 parts per million. So you can see we have these signals here, A, B, C, and then you go all the way down here and you see this little signal, okay? And that would be the carbonyl carbon because you see that it's at around, well, it's pretty close to 210 parts per million. And so those are really the only signals we see that high up in the carbon spectrum are going to be a carbonyl carbon around 200. And so did we learn a lot of reactions in this chapter? The answer is absolutely. We talked about the formation of a hydrate. So you should know about the formation of a hydrate, an acetal, a cyclic acetal. Then we looked at a thioacetal, and we talked about how you could reduce that with rainy nickel. That's called desulfurization. Then we looked at imine formation. We looked at enamine formation. We talked about oximes rather. Sorry, this is an oxime, which is made from hydroxylamine. Anyhow, getting ahead of myself there. Then we looked at hydrazone formation, and we talked about the Wolff-Kishner reduction to reduce the hydrazone down to an alkane. What else? We talked about lithium aluminum hydride reduction. We talked about Grignard chemistry, cyanohydrin formation. We looked at the Wittig reaction, and then the last one that's shown here is the Baeyer-Villiger oxidation. So a lot of chemistry in this chapter, and make sure you know all of these reactions very well.